So, metamorphism. So we're going to talk about the first type of rocks, and the first type of rocks is metamorphic rocks. So I wanted to mention that meta means to change, morphism means form or shape. So these are changed rocks that we're talking about. And so there's changes, and they come in three ways. Typically, the rock's texture changes. Typically, you get a new set of minerals, so we get a new mineral composition. And the third way is that we have a volume decrease. So the rock literally gets smaller in size with a higher density. The three things that cause the changes in metamorphic rocks, which we call change agents, is heat, pressure, and hot chemical fluids. And when I say hot chemical fluids, I'm talking like really, really scalding hot water. Typically, metamorphism occurs in the first layer of the Earth, which is the lithosphere. So it usually goes from slightly below the surface, around 2 kilometers down, all the way down to the Moho, which is called after Mohorovici, and it is the boundary between the lithosphere and the all three types of rocks can be metamorphosed. So an igneous, sedimentary, and even a metamorphic rock can be metamorphosed even further. So all three types of rocks can be metamorphosed. For example, granite is an igneous rock that gets metamorphosed to a metamorphic rock called gneiss. Sandstone, which is sedimentary, goes to quartzite, which is metamorphic. Slate, which is metamorphic, can go to schist, which is also metamorphic. So this is just proof of the fact that an igneous rock can be metamorphosed, a sedimentary rock can be metamorphosed, and a metamorphic rock can even be metamorphosed even more. The most important thing that I'm going to say is that you cannot say the word melting when you're talking about the formation of a metamorphic rock. It does not involve a melt. The minute when you say the word melt, it implies molten, and molten is lava or magma, and so all of a sudden you're back to igneous rocks. We're talking about forming metamorphic rocks, okay, not igneous rocks, so we cannot ever use the word melting. That's why it's so important that every single time you talk about change agents, you talk about heat, pressure, and hot chemical fluids. It's actually the hot chemical fluids that serve to dissolve away the minerals that exist in the parent rock, and minerals are made of compounds and compounds are made of elements. So then those elements are free moving in that hot chemical fluid, and they're able to reform into new compounds and new minerals in the metamorphic rock. So no melting, but instead the presence of hot chemical fluid. One of the ways that the rock can be changed is by texture, and there's two kinds of texture, foliated and non-foliated, so it's pretty simple. Foliated means banded. We don't want to say layers, and the reason why we don't want to say layers is because layers make people think about sedimentary rocks. So we're going to go with banding, and if you were to look down here, you can see that all the minerals are lined up in a line, in bands, and we call that foliation. The rock that you're actually looking at in this picture is a rock called gneiss, so Gneiss, and gneiss is a foliated metamorphic rock. To the right, we have a non-foliated metamorphic rock. This rock is marble. Marble is metamorphic, of course. It's non-foliated, meaning that the actual crystals of the minerals that make up this rock called marble are not in a line, okay? So you can see that the two are very different pictures. One has these bands and one doesn't. So we talked about every time a rock gets metamorphosed, we have a volume reduction. So if you think about it, one of the causes or change agents is pressure. So when the rock gets exposed to so much pressure that it basically causes that rock to have an increase in density and a decrease in volume. The other one is you're actually going to get a chemical change. So the minerals that you have in your metamorphic rock, they could possibly be the same as the ones that were in the rock before, or they could potentially be different. But at the end of the day, they are new minerals that crystallized from the hot. What you're looking at in this particular diagram is the two textures. So if you were to focus on this diagram, this is before metamorphism. So let's pretend that that's an igneous rock called granite. You can see that the crystals are all over the place. After metamorphism, you can see that the crystals are more in alignment like this, so you can see the idea of banding, okay? Because granite is one rock that gets metamorphosed to gneiss, and gneiss is foliated. So if you were to look at the picture on the side, right here inside of granite, which is like this rock, the minerals are all over the place, and if you were to look in gneiss, which is this rock, you can see that they all line up in these really nice bands, okay? So that's foliation. Non-foliated, there's only two rocks that are non-foliated, and that's quartzite and marble. And if you look at the graphic below, you can see that if you were to look inside a quartzite, there is no foliation at all. So the pairs that you need to know for the course is limestone, which is a sedimentary rock. That gets metamorphosed to marble, and marble is metamorphic. one of the things that I wanted to point out is that marble is LG, which means it's a low-grade metamorphic rock. Sedimentary sandstone, so if sandstone gets metamorphosed, it goes to quartzite. Quartzite's metamorphic rock, but it's also low grade. Sedimentary rock shale goes to slate. Slate is low grade. It can go even further to phyllite, and that's a medium grade. It can go even further, and that's schist, which is a high grade, and it can go even further to gneiss, which I say is extremely high grade. So it's possible to take a sedimentary rock like shale, make a metamorphic rock, an even higher grade metamorphic, an even higher grade metamorphic, and an even higher grade metamorphic rock. Similarly, you can take the igneous rock granite, and granite can be metamorphosed into gneiss, which is also an extremely high grade metamorphic rock. So as you can see, there's two ways you can get to gneiss. You can get there by a sedimentary rock called shale, or you can get there by an igneous rock called granite. There are two different types of environments that you can have for metamorphism. You can have contact metamorphism, which we talked about in Unit 2. Contact metamorphism is the type of metamorphism we call baking or burn marks. You need all three. You need heat, pressure, and hot chemical fluids, but clearly heat is the most important factor because the rocks are being baked. Typically they get baked by like really hot lava or really hot magma or like friction due to a meteorite impact. The other type of metamorphism is regional. If you think about the word region, it's a large area, so it typically relates more to mountain building or subduction zones, which are highly connected to the formation of mountains. With regional metamorphism, because it typically occurs at the base of mountain systems, we realize that all three are also important, meaning heat and pressure and hot chemical fluids, but pressure would certainly dominate in that particular case. In this particular diagram, we're looking at contact metamorphism. So if you were to look at the diagram on the left, and if you were to look at B is a magma intrusion because there's X's on top and bottom. R is a lava extrusion because there's X's on the bottom only. When we talk about magma intrusions, there's two words that we need to use. We need to talk about a sill and a dike. So really, a magma intrusion that's more lateral, like more on the side, is called a sill. So just think about like a windowsill. You can actually rest your arm on and lean on a windowsill because it's flat. So in this particular case here, the magma moves in from the side, a nice horizontal magma intrusion, and it bakes the rocks all around. So we could easily put X's here. They don't have X's. They have this little symbol that I've never ever used before. Still means the same thing. In this particular case, the magma intrusion is basically straight up and down, so it's more vertical, and because it's more vertical, we call this a dike, and typically you would get X's all around the sides. Like that, okay? So basically, it's just a magma intrusion, and so you're getting contact metamorphism. I'm just stating that if the magma intrusion is straight up and down, it's called a dike. If it's sideways, it's called a sill. A buried lava flow or a lava extrusion we learned in Unit 2 is when you have the X's or the baking on the bottom only, and a magma intrusion is when you have the baking or the X's on top and bottom. Moving on, regional metamorphism we said occurs in mountain building, and so really far down at the base of mountains, and that's typically how you get the largest amount of metamorphic rock would be in this type of environment. You also could get it in subduction zones. Subduction zones are typically defined by one plate going down in under another plate, and so it happens in a lot of different areas of our world. You can get it where an ocean collides with a continent, or where a continent collides with a continent, or where an ocean collides with an ocean, and we call that a convergent plate boundary. So that's typically where that takes place. There's a lot of compression, so pressure is high. Pressure is high due to compression, but pressure is also really high due to the depth of burial. So with the depth of burial, we also get increasing looking in this particular diagram here, what you can see is a convergent plate boundary. So we got a plate going this way, and we have a plate going this way. This is typical of what you see in the Himalaya Mountains. So let's pretend that these are the Himalaya Mountains, including Mount Everest. This here could be like China, the Tibet Plateau, and this here would be like India. So they come together, and you also got to remember, before they came together, this would have been an ocean right here, and on the side of every single continent, there's a continental shelf. So what you're actually looking at here is sedimentary rocks that have been pushed up from the continental shelves of both continents. And so all I'm trying to show you here is that in this particular place, if you had a sedimentary rock called shale, and it went to here, you would get slate. If it went to here, you would get phyllite. If it went to here, you would get schist. If it went to here, you went gneiss. So this is the sequence to show how a sedimentary rock can get metamorphosed, but then also can get metamorphosed to a higher grade. So here we have a slate, low grade, medium grade, phyllite, high grade, schist, extremely high grade, gneiss, which is down in the plate boundary. This is the same thing, but represented in a different way. So basically, anywhere around here, you can get X's around all these little magma chambers is where you get X's to represent the baking, which is the contact metamorphism that's being caused by the magma. Now, why do we get the magma? Because this plate comes down here, and this plate melts down here, creates magma that goes up and actually bakes the rocks around it. It's hard to say where we would get regional metamorphism to here, because in this particular diagram, the continental shelf is really, really small. Essentially, if you had shale here, it could go down here to become slate, go down here to be phyllite, go down here to be schist, go down here to be gneiss in this little zone. But clearly, this is a very, very small continental shelf. If the continental shelf was bigger, I could easily show you where you could get that sequence of changes inside of metamorphism. So slate is low grade, phyllite is medium grade, schist is high grade, and gneiss is extremely high grade. So this is about rocks being different grades. So here's your shale, goes to slate, low grade. Here's your granite, goes to gneiss. Gneiss happens to be an extremely high. Which feature is represented by X's in the diagram below? So if you were to look at these X's in the diagram below, we simply know that X's mean baking, which is also means contact metamorphism. Just don't ever associate baking and X's with regional metamorphism. That would be a no-no. One thing that I wanted to say is, imagine on a public exam if there was a question that said, what kind of rock would you get here at location A? Now, these dots, as you know from Unit 2, dots represent sandstone. So think about it. If you have sandstone and the magma comes in and the magma bakes the sandstone, the question is, what will sandstone become if it gets metamorphosed? So the answer to this question would easily be quartzite. Similarly, if you didn't have sandstone in this particular area, and instead if it was limestone and the limestone got metamorphosed here, then you would expect marble in that particular case. So be prepared for both of those type of questions on the unit test. Which rock was subjected to the highest temperature and pressure conditions? Well, naturally, you're going to look for your extremely high-grade metamorphic rock, which is gneiss, and gneiss is here, so I'll pick it. Marble's low-grade, slate is low-grade, shale's not even a metamorphic rock. This is a sedimentary rock, so it's there as a different careers that you can take in terms of metamorphic rocks. Petrology studies rocks, volcanology studies volcanoes, geochemistry studies the chemistry of the earth, meaning the chemistry of rocks, minerals. Sedimentologist looks at all the different types of sedimentary rocks, and hydrologists study the water down inside the earth. And I'm trying to really sell the message of the importance of hot chemical fluids to the process of metamorphism. So in that particular case, hydrologists would be really important.